Hi, my name is Archana Shrikanta. I'm a principal engineer in AWS. I started out on EC2. I spent a couple of years there. And then now, for the past 6.5 years, I've been involved in the container space. Specifically, my area of focus is serverless containers. I was the first engineer, the founding engineer of Fargate, and now most recently I've been involved in the design and execution of App Runner. So today we're going to do a deep dive on App Runner, starting with the general introduction of what App Runner is and the application types that are best suited to run on App Runner. And then we'll walk through a little bit of a history of the compute services that we've built on AWS to understand why we built App Runner and where it fits in that spectrum of compute services. And then we'll actually walk through the experience of building an application on App Runner with the demo. And then we'll deep dive into some of the key differentiating features of App Runner. And finally, we'll close with a discussion on how pricing works with App Runner. So let's get started. So App Runner is a brand new AWS service. It was only launched last month, and it's a service that provides a highly abstracted, simple, managed experience for running your web applications or API servers. And we'll get to all the things that are magically abstracted away by App Runner in a few minutes here. But before we do that, let's understand a little bit more about the applications and the properties of applications that are best suited to run on App Runner. So as we just mentioned, this is suited for web applications, front-end servers, back-end servers, basically any application that is an HTTP request reply based service. Now, the application must be written as a traditional long-running server where a single copy of your application can serve multiple requests during its lifetime, even simultaneously. So this is not like a Lambda function model where a single invocation of the function handles a single request and exits. This is the more traditional long-running server model. And the application must be stateless in that any request processing that you perform should not depend on any local state being present on disk. If you do need to store state, you can use external databases and data stores that your application can connect to. And finally, background processing should be limited to little or nothing. And by background processing, I mean any processing that happens outside the context of a request. So any offline processing should be avoided. And we'll talk about why these properties are important as we go through the content here. All right, so why did we build App Runner? And to understand why we built App Runner, let's look at the typical architecture for such an application that we just talked about. Um, so you typically start with the virtual machine. You install a guest OS inside the virtual machine. You install a language runtime of your choice, and then your application runs on top of that. Now, if you're running this at production scale, you're probably not running just a single copy of this. You're running multiple copies of the stack for scale and redundancy, which means you have to front it with the load balancer, you have to put an autoscaling group around it, and you probably have some kind of CI/CD pipeline to push changes and updates to this application. And if you've run applications on AWS, you might be familiar with the shared responsibility model on AWS. And the essence of the shared responsibility model is that the security and general operational stability of your applications on AWS is a shared joint responsibility between us, AWS, and you, the customer. And this shared responsibility looks different for different AWS services, and it has evolved as we've launched newer and newer services on AWS. So, starting with EC2, which is the first original compute service on AWS that was released way back in 2006, what what does the shared responsibility model look like for EC2, right? So with EC2, we said AWS will take responsibility of the physical servers that are running in data centers and the virtualization stack that's running on top of these physical servers. You, as the customer, you can just make an API call and basically spin up virtual machines in the cloud, what we call EC2 instances. And as the customer, you continue to own all the software that's installed within your EC2 instances, including the guest operating system and the language runtime. Um, and of course, you are responsible for hooking up the load balancer in front of your instances, the autoscaling group, and any CI/CD build deployment pipelines to push changes. And from a pricing perspective, you're paying for provisioned resources, meaning you're paying for the load balancer and the EC2 instances, irrespective of whether your service is actually receiving any requests and doing actual work, right? And then in 2011-ish, we realized that hooking up all of these individual components together and building this kind of ecosystem around your application is not an easy job. And so we launched Elastic Beanstalk. And what Elastic Beanstalk did was that it was a place where you could orchestrate all of these components centrally. So it provided a single kind of management pane, so you didn't have to go and individually stitch all these resources together to build your application. But the resources themselves continue to run in your account. And as the customer, you still have full access to all of these individual components. So, in that sense, we still rely on you as the customer to operate the stack responsibly. And from a pricing perspective, not much changed. You continue to pay for your load balancer and EC2 instances as provisioned resources, irrespective of actual work done. And then a few years later, we noticed that containers were starting to become popular. And what customers were doing was they were decoupling the application from the operating system within the EC2 instance. So they would bundle the application and the language runtime into container images and deploy the app as containers within EC2 instances. And in order to manage these containerized applications at scale, the typical model is that you install an agent locally within the EC2 instance. The agent then talks out to a much beefier container orchestrator control plane. And customers were actually running this entire setup themselves. Like they were running and installing and running container orchestrators on their own EC2 instances and managing it. And these container orchestrators, if you're familiar with things like Kubernetes or Mesos at the time, they're pretty beefy pieces of software to run and manage. And so in 2015, we launched Amazon ECS, Elastic Container Service, and that basically moved this container orchestration layer down below the boundaries. So AWS took over responsibility for container orchestration. But of course, you have to continue to hook up the load balancer, autoscaling group, CI/CD, deployment pipelines, all of that. You still have to kind of hook it all up together to make your application work end to end. And again, from a pricing perspective, nothing really changed since all these resources are still running in your account. You're still paying for the load balancer and the EC2 instances as long as they're running. And then in 2017, we looked at the landscape and we said, we think we can do more. And so we launched AWS Fargate. And Fargate is basically our serverless containers platform. And what Fargate did was it raised that abstraction boundary even higher. Um, and so with Fargate, AWS now owned running the EC2 instances and all the kind of base layer software on these instances that are outside of your containers. So the operating system, keeping that patched and secured, any agents and container runtime. We owned the interaction between the agent and the container orchestrator control plane. So you, as the customer, you're only dealing in the currency of containers. You don't see the VM layer at all. But even at the container level, you do have to attach the load balancing, auto-scaling, CI/CD components to your architecture. And from a pricing perspective, you no longer see the instances, so you're not paying for the EC2 instances per se, but you're still paying for provisioned resources at the container level. And this is still provisioned resources in the sense that you're paying for the CPU and memory for your containers irrespective of request traffic to your service. And now with App Runner, what we're doing is we're raising that boundary line even higher. So not only are we handling kind of the VM layer, EC2 instance layer of the fleet, we're also taking over responsibility for actually deploying and running your containers and the language runtime that's within them, keeping that patched and up to date and secure. We're also taking over responsibility of load balancing, the load balancing infrastructure to distribute traffic across your containers. We're taking over responsibility of automatically scaling your containers as your traffic moves up and down, and also build and deployment infrastructure around your containers. So you, as the customer, can truly just focus on writing your application, and all of these ecosystem components, not just the compute layer, all the peripheral components are now handled behind the scenes by App Runner. With App Runner, you're paying for resources when your application is actively processing requests. We do have a concept of provisioned resources, which we basically keep up and running and warm to avoid cold start latencies, and those do incur a nominal fee, but um, it's nowhere close to running a full EC2 instance or a full Fargate task. And I can tell you that a lot of the sort of technical muscle behind this project has gone into really figuring out how we can shrink the resource footprint of these kind of provisioned idle instances, and thus shrink the cost so you're truly only paying during request processing. All right, so now let's walk through the experience of how you would build an application on App Runner. So you can either start with source code in a GitHub repository, or you can also bring your pre-built container images to App Runner. You can push them to ECR and make that your starting point. Either way, you have to give AWS permissions to access your artifacts in either GitHub or ECR. So if you start with GitHub, your first step is to create a connection, which basically authorizes AWS to access your source code in GitHub. Or if you start with a container image, you have to create an IAM role that gives us permissions to pull your image from ECR. And then once you've done that, really it's just a single API call. It's the create service API. You give us your build and runtime configuration. You configure CPU memory size for your application. There's some basic health check, auto-scaling deployment config, and it's just one API call to get your service stood up. And out you get a service URL um, in the response against which your clients can start to make HTTP requests. And within your account, you will see no EC2 instances, no Fargate tasks, no auto-scaling group, no load balancer, none of that. So let's jump over and actually do a demo here of the service creation. So this is the App Runner console. So we're gonna, well, before we start with the create service, let me show you my GitHub repo. So this is my GitHub repo. This is just a very simple Python application. It's a Flask application, and all it's doing is it's listening on port 8080. It's looking for an environment variable called name, and then when you make a request, it's just going to print hello followed by the name. So let's jump over here and start to create the service. All right. So there's 3 steps here. I guess we go to there's 3 steps here. The first step, you will configure the source code repo and give us permissions to access it. In the second step, you will give us all your build commands. And in the third step, it's all the runtime configuration of your service, and then we'll create the service. So in the source and deployment section, we're going to start with source code repository. You can also start with the container image if you so choose. And then this is the create connection step. Now, I already have a few services running against this repo, so I already have a connection. It's a one-time step you need to perform per repo. But if you were doing this the first time, I'm just going to walk through the steps you would take here. These fields would not be populated, and you would click on add a new connection, and that will bring up this pop-up window and walk you through the connection creation process. So you can give your connection a name, and you will have to install a GitHub app here. So if you click on install, it will ask you to log in to your GitHub account and take you to this page, which is the AWS connector for GitHub. And this is the application that you will install that basically gives AWS these read-write permissions to your repositories. And you can select if you want to give these permissions to all repositories in your account, or you can just select the specific repository of interest. And then once you're done with this, you can close this window and jump back here. These fields should get auto-populated. Deployments wise, there are 2 options, and we'll talk more about this in future slides, but you can either pick a manual deployment, or you can choose to auto deploy every time you push to your GitHub repo. So moving on to your build settings, if you noticed here in my repo, I don't have any Docker file or any build related file here at all. And that's because I can actually provide all my build commands right here in the console in the App Runner API. So let's go ahead and pick a language runtime. In the build command, I am going to install the dependencies. And then to start my server, we'll say python server.py. And then the port that your application is listening on. And that's really it. And now the runtime configuration. Let's give this service a name. You pick a CPU and memory size for your application. We're going to go ahead and add an environment variable called name. So this is what the application looks for. Let's say demo. And then there's some autoscaling configuration. Again, we'll talk more about this when we're in the autoscaling section, but I'm going to leave it as the default here. You can configure health checks, you can add tags, and that's really it. So you review and create your service. So as soon as you create it, you see it goes into operation in progress, and you already, you have a domain URL that's returned here to you. Once this service is created and goes to status running, we'll be able to actually hit this URL and see responses back from the service. So the service creation takes a few minutes here, the initial bootstrap. So while this is in progress, let's jump back to the slides, and then we'll come back to this and check what happened here. So now let's look at a little bit more about the compute, networking, and storage landscape around your App Runner application. Terminology-wise, I'm going to use the term application instance to mean a running copy of your application. It's not to be confused with EC2 instances. It's a separate concept. So behind the scenes, what App Runner is doing right now is that it's actually pulling your source code, building a container image out of it. It's layering the language runtime that we curate and manage along with your application, building a container image, and then we actually deploy your images as Fargate tasks behind the scenes. And as I mentioned, a single running copy of your application is what we call an application instance here. And as you noticed, we had to pick a CPU and memory size for the application instance. You can pick from any of these valid combinations here to the right. And you also configured the max concurrency, which is basically the maximum number of simultaneous requests a single copy of your application can handle. So it's not requests per second, it's how many simultaneous parallel requests your application instance can handle. And behind the scenes, behind the service URL, as I mentioned, App Runner is going to spin up multiple copies of your application instance. It's going to scale it up and down as the traffic demand changes. And as your requests come in, we'll distribute the load across all these copies of your application. And these application instances that are actively processing requests are, we're going to call them active instances. Um, and as we kind of scale your application up and down, there may be certain scenarios where we preemptively spin up an application instance, um, and it may not yet be processing any requests. We may not be directing any requests actively to that instance. In that case, it's an idle instance. And these idle instances, the thing to note about these idle instances is that they may be resource throttled, meaning that they may not have access to the full CPU allocation as you configured it in your service, which is why it's important to make sure that you don't have any of that background processing that's happening outside of the request context. Once the request starts hitting this application instance, it becomes active and then it gets access to its entire CPU and memory quota. But if it's idle, it may not have access to its full resources. And from a concurrency perspective, concurrency is the dimension that we use for scaling. So the number that you set here can have an impact on the cost that your service incurs. So for example, here, if you set the concurrency of your service to 10 and you send 30 requests to your service, 30 concurrent requests to your service URL, we're going to spin up 3 copies of your application to handle that load. And you're going to pay for the CPU and memory associated with all 3 of these application instances. Versus if you set your service concurrency to be 30, we really only need 1 copy of your application to handle the 30 concurrent request load, and you're only paying for the CPU and memory of a single application instance. So you really want to do some homework to figure out kind of that sweet spot for your concurrency, where it really is the maximum load that your application can handle at a given point in time reliably without falling over. Networking wise, the service URL that you get after you create a service, it's a public internet facing endpoint, so you can access it from anywhere. And egress wise, the application instances that we spin up behind the scenes, they all have outbound access to the internet. You don't have to set up a VPC or an internet gateway or NAT gateway, any of that in your account. It's all running within a service managed VPC behind the scenes. Um, in the future, on the roadmap, we do have items to support private services. So it's a private non-internet facing endpoint in your VPC. And egress wise, we're going to support outbound access to VPC resources. So your application instances, if they need to talk to other private entities within your VPC, we will allow that via outbound VPC access. So these are things that are on the roadmap to come. Storage wise, each application instance is given 3 GB of disk space. And this will include any storage that is consumed by the container image layers themselves. So that's something to keep in mind. And also, the most important thing is that the storage is ephemeral, meaning that if the application instance is spun down, the storage is gone along with it. The storage doesn't exist beyond the lifetime of the application. And since we're doing the auto scaling behind the scenes, we can choose to spin your application down at any time, and your request may go to a brand new application instance. So don't expect any local state. on the instance when you're request processing. All right, so let's go and check on that service creation and see if it's spun up. All right, create service succeeded. And so now you can see the status here has flipped to running. And if you hit this URL, you'll see hello demo, and the service is actually up and responding. All right, so now we're going to start to deep dive into some of the kind of key differentiating features of App Runner. We'll start with autoscaling. So autoscaling wise, there are three knobs that you have, three settings that you can use to guide the autoscaling algorithm that we use behind the scenes. We talked about concurrency. There's also a minimum and a maximum instances that you can set. The minimum is basically the number of provisioned instances we will keep up and running behind the scenes, even when your service is idle, so you can avoid kind of cold start latency effects. And as I mentioned, there is a cost associated with these, but you can set a baseline for your service to avoid cold starts. And the maximum is basically an upper bound on the number of instances so that when we do scale out, you can control the cost that your service incurs at peak load. So now to understand how the autoscaling dynamics occur behind the scenes, we're going to walk through an example here. So here I have a service with a concurrency of 30, a min of 3, and a max of 5. And when the service is idle and no requests are coming in, we basically spin up the minimum number of provisioned instances, which is 3 in this case. And they're all idle, so they may all be in that kind of resource throttled state. And now we start to put some load on this service. Let's say we start by throwing 20 concurrent requests at this service. And because 20 is kind of less than the concurrency of a single instance here, which is 30, we're basically going to activate one of those provisioned instances, and a single instance is enough to handle the 20 concurrent requests. So let's see this in action. So let's hop over here to the demo. So what I've done is I've pre-created a service here just for the autoscaling demo. Let's go in there. If you look at the configuration for this one, autoscaling settings, we've set concurrency of 30, min of 3, max of 5. And now here I have a local tool here, which is just a request load generation tool called Hey. And the parameters here are -c, which stands for concurrency. So we're going to set that to 20, and -z, which stands for duration. We're going to run this load test for 60 seconds. And let me copy the service URL here. And paste that here. So what the tool is going to do is it's going to spin up 20 worker threads, basically parallel threads. And these threads are just going to constantly loop and send requests, HTTP requests to this endpoint for 60 seconds. And while this is happening, let's jump back to the slides. We'll come back and check on that demo, but it's going to go for a minute or so. So let's continue with our example. So we saw what happens when we sent 20 requests, single instance got activated. Now, what if we up the load to 75 concurrent requests? So with 75, we basically need all three of the provisioned instances to handle that load. So we'll activate all three of those instances and distribute the load across all of them. Also, at some point, when we start to see that the existing provisioned instances are starting to run hot, so in this case, for example, the capacity of each instance is 30 concurrent requests, and we're already running at 25, App Runner behind the scenes will start to provision additional instances. Now, don't put too much weight on the exact numbers. Your mileage may vary, but this is really for illustrative purposes to show you that at some point before you hit capacity on all of the provisioned instances, we will start provisioning new instances behind the scenes. And in case your ramp up, like let's say you ramp up from 75 to 100 concurrent requests in a very steep way before we can react and actually provision the new instance, then what happens then? We will max out any existing provisioned instances. So in this case, we'll send 30 requests to all the existing instances and max those out. And then the additional requests, which is 10 here, will get queued behind those existing instances. So this is where you may start to see some of the cold start latency effects. But as this new instance gets provisioned and it comes up, and if you're still sending kind of the load at 100 concurrent requests, it will even out, and then the new instance will come up and start to take some of that load, and the cold start effects should subside as we bring up new instances. So I'm going to do a kind of a second load test of 100. So let's see. So this one completed. So this was our load test of 20 concurrent requests. As you can see, all the requests succeeded. We got 200 responses. So now let's go in here and kick off a load test with 100 concurrent requests. And we're going to run it a little bit longer to give the service some time to react and bring up those additional instances. So let's kick that off. It's going to run for 3 minutes. And in the meanwhile, you can see what actually happened behind the scenes autoscaling wise by looking at the metrics tab. So here in the metrics, we have some interesting metrics here. The first chart here is the request count, which is just the raw number of requests. You can see the spike there from our first load test. There's response codes, request latency, and then this is the interesting one, autoscaling wise. It's the active instances metric. And you can see here when your service is idle, we're at 0 active instances. But as soon as we hit the service with the load of 20 concurrent requests, we basically activated 1 instance to handle that load. All right, so now while the second load test is still ongoing, well, let's continue with our autoscaling example here. So we saw what happens when we did 100 requests, right? We had to bring up this 4th provisioned instance. Now, what if you continue to raise the load to 200 concurrent requests? At 200, we're basically going to bring up that 5th application instance, at which point we've hit the max. So we've maxed out as much as we can scale out. We're going to send 30 requests to all of these, but we're still only at 150 concurrent requests. So the remaining 50 requests will get queued behind all of these existing instances, but of course the queue, it's just a finite buffer, so you may even see some dropped requests because we can't actually scale out any further. So hopefully that gave you a good idea of kind of how the autoscaling algorithm works behind the scenes. And now we're gonna move over to the next feature that I wanted to demonstrate here, which is that of deployments. So deployment-wise, we saw this when we were creating the service. There were 2 options. You can choose to opt into auto deploy, which means every time you make a code commit to your GitHub repo, or if you're starting with a container image, every time you push a container image, App Runner will automatically pick up that change and deploy it out to your application. Or if you don't want to opt into that experience, you can also use the manual trigger start deployment API to hook it up to your own CI/CD pipelines. And either way, what we do behind the scenes is we do a blue-green deployment, which means we'll spin up new copies of your application against the new version of your code, run the health check, make sure they're up and healthy, and then flip your traffic over from the old version of your code to the new version of your code. So you should experience no downtime there. And also, if we notice that your health checks are failing on the new version of your code, then we will automatically roll back and spin down kind of the new application instances that we spun up. So let's see auto deploy in action here. So before we jump there we go. So this is our auto scaling load test with 100 concurrent requests. As you can see here, there were a few dropped requests. This is because we kind of provisioned beyond that min provisioned instances, and we did scale up from nothing to 100 concurrent requests pretty steeply. So there was some cold start effect there. And metrics wise, there we see the request count spike up, and the active instances here basically spiked up to 4 active instances to field those 100 concurrent requests that we were throwing at it, right? And min provisioned was 3, so we actually did scale up to 1 more instance beyond your min provisioned number. Cool, so that was the auto scaling demo. Now over to the auto deployment demo. All right, so for the auto deploy demo, I have a service that I pre-created here. And if you look at the deployment settings, I have enabled automatic deployments on this service. So what I'm going to do is let's hit this URL first to see what the service is returning. And it says hello auto deploy because the environment variable here that I set for name was auto deploy. So what I'm going to do now is I'm going to go into my GitHub repo and make an edit. So let's see. Instead of hello, let's say good morning here. Take greeting. And then we'll commit the change. And then if we hop back over, so you can see deployment is already in progress here on my auto deploy demo service. So the status flips to operation in progress and a deployment is ongoing. So let's give that a couple of minutes and wait for that deployment to complete. We'll hop over here and continue with the presentation. All right, the next feature I wanted to talk about was observability. Observability wise, we're going to cover logs, metrics, and events to help you see or understand what's going on behind the scenes of your App Runner service. So logs are delivered to CloudWatch. We publish 3 types of logs. The first one is what we call deployment logs. This is basically the build output. And then there's application logs. These are the logs that are actually emitted by your code. And finally, we have event logs. And this is basically a log of all the operations that that App Runner performs behind the scenes, and it's especially insightful during service creation or during deployments when there's a lot of things going on behind the scenes to give you some insight into the progress of the service creation and deployments. So we can actually hop over to the console here and check out the logs. So this is the demo service that we created. As you can see now, it's up and running. And logs wise, so top one is the event log. So this is the life cycle operation. So as you can see here, service creation started. We successfully pulled your code. We're starting to build your code, successfully built the code. We're provisioning the instance and deploying the image. We're performing the health check passed. So we started to route traffic to your application. And that's when service creation completed successfully and the status was set to running. So these are kind of the life cycle events behind the scenes. So these are the deployment logs, which is the build output. So if you click into that, you can see here we installed the dependencies. We're pulling down all the image layers and building your container image here, and we've successfully built your container image. And finally, application logs, as I mentioned, was the logs that's actually emitted by your code. And this is what this looks like. So you can see here, the application printed a log message saying, I returned hello demo. So those are the logs. Metrics-wise, we already looked at some of these. We have CloudWatch metrics for request count, the latency of your requests, the various HTTP error codes that were returned. And then we also have a metric for active instances to show you the number of application instances we scaled up to process your incoming request load. Typically, this active instances metric will be useful if you want to correlate it with your bill or understand kind of the costs that your application is incurring. And events wise, we do deliver any status change events on either service creation, updates, or deployments to Amazon Event Bridge. And you can use these events if you want to hook up kind of rule-based automated actions that you want to take in targets like Lambda or ECS or SNS. And we also log all the App Runner API calls that you're making to CloudTrail for auditing. All right, so before we go into the final section, let's go check on our auto deployment demo and see if that deployment succeeded. So there we go, auto deploy demo, it's now running again. And now if we hit this URL, it says good morning auto deploy rather than hello auto deploy. So it has successfully picked up that change that we made. All right, so finally, these are just a few other kind of more advanced features that we have in App Runner. I'm not going to go through a demo for each of these, but I just wanted to touch upon these to let you know about them. We have support for custom domain names. You may have noticed that the service URL that we provide to you, it's under the App Runner domain, but if you own your own domains and you want to associate custom domain names, you can do that. You don't have to manage any of the certificates. We manage that for you behind the scenes. Data encryption at rest. So all the source code or the images that we pull and store behind the scenes for your application, all of that is encrypted at rest using AWS managed keys by default. But if you're opinionated and you want to provide your own keys, you can provide KMS keys, and we will use that to encrypt your artifacts behind the scenes. We also have a feature to pause your service. And this is useful, let's say you have a dev environment and you're using it during your workday, but when you go home in the evening, you basically want to shut the service down so it's not incurring any cost during that period. You can pause your service, and when you pause it, we basically tear down all the resources associated with your service, including the provisioned instances, so you're not incurring any cost. And then when you come back in the next day morning, you can resume it and turn it back on, and it just takes a few seconds to bring everything back up. And finally, pricing. So let's see how all of these features are priced. We have a couple of different dimensions for pricing. The first dimension here is the CPU and memory of your application instances. And the way this works is as long as if your instances are active and actually processing requests, you pay for the CPU and memory associated with those instances. But when your service is idle, you only pay for the memory of any minimum provisioned instances you may have. And we'll walk through an example here to understand the CPU memory pricing in a bit. But the other dimensions for pricing are build fee. So there's a $0.005 dollar fee associated with every build minute. So as long as your application is building, we will charge you $0.005 per minute. And this obviously only applies when you're starting with source code. It does not apply if you're starting with a container image. And if you do opt into the automated deployments that we just saw, there is a $1 fee per service per month. And finally, data transfer wise, any data transfer in and out of your application instances will incur the standard AWS data transfer fees. So back to the CPU memory pricing, what we're going to do here is we're going to take that autoscaling example that we saw and kind of superimpose how the pricing looks on top of that. So this is, starting with your idle state when there's no request to your service, we've spun up the 3 minimum provisioned instances. And as I mentioned, when there's no load on your service, you're only paying a very nominal fee for just the memory of these idle instances. Now, let's say you added your load, your first step of 20 concurrent requests. We activated one of those instances. And now, in addition to the memory of the provision instances, you're going to start to pay for the CPU of this one active instance. And then as we ramp up the load to 75, we're going to activate 3 instances. Now, all 3 are processing requests, so you're going to pay for the memory and CPU for all of these 3 instances. And as we start to dynamically provision more instances over and above your min provisioned instances, as I mentioned, we may do this preemptively. Um, but if we do spin up dynamically provisioned instances on top of the min, you're not charged for those instances as long as they're idle and not actually processing requests. It's only when you start to increase the load and we start to put that fourth instance in service, at that point you will start to see a charge for the memory and CPU associated with those dynamically provisioned instances. All right, so that's really all I had, and the prime takeaways from this session that if nothing else you want to take away from here is App Runner is a service that's really built to give you an extremely simple managed experience for running your HTTP-based services. Your containers, your language runtime, the load balancing, auto scaling, CI/CD, all of that is taken care of behind the scenes, so you don't have to stitch all of those components together yourself. And pricing wise, you're not you're just paying by use only when your application is actually processing requests. um, we do have a public roadmap that's available on GitHub, so definitely go check it out to see what features we have on the roadmap. You can add new feature requests, you can upvote existing feature requests, and yeah, definitely get started with your app on App Runner and give us your feedback. Thank you.